there, and the law of reflection still applies. So light doesn't converge, light diverges. And this is where the weird part of optics comes in. The light diverges. Does that mean no image forms? If you have light, if light has to go to your eye to have enough information to create an image, does that mean if you look at a convex mirror you see nothing? No. You see what's called a virtual image over here. And we're going to talk more about virtual and real here in a second. Okay. Now, first of all, another little bit of lingo. The principal axis is what we set the mirror to. We always set our devices perpendicular to the principal axis because it makes life so much easier. So this is the principal axis. We set our device, our mirror, perpendicular to the principal axis. Hang in there, Aiden. You'll have time to clash your clans in Spanish class. Or play your busty Chinese RPGs.
Busty Chinese what?
RPGs.
I think he's talking about Raid Shadow Legends.
That could be.
Probably.
Download them, they're free. And now someone's in your phone. You are now part of a botnet. Congratulations. I always wanted to be part of something.
Not China.
Hey, I'm part of something. I'm part of a botnet. All right. So that's principal axis. Okay, how are we doing? Are we okay? All right. Now, it wouldn't be physics without, oh, sorry, there we go. Focal point, focal. So there's focal point. Where is the focal point of a convex mirror?
Would be past
Nowhere.
It's back here.
Oh.
It's back here. Now, this is important. Are you ready? So the focal point of a convex mirror is right there where these guys go, okay, like I said, it's right there. Like I said, it's right there where the rays converge. But light rays don't converge. Now, this is one of the weirdest things in optics, and you just kind of have to wrap your head around it. Your brain is really good at taking in a lot of data and creating images.
That's neato.
Yeah, your brain is not easily fooled. Some species' brains are easily fooled, but not yours. So you're taking in a lot of information from this side, and your brain's saying, no, the image is not over here, it's back here. And because it is not where the light is, we consider it to be a virtual image. Virtual. Right? Now, not real, just created with information that is not there. Yeah.
So are you saying, like, since the light's not traveling directly at our eyes from that mirror right there, we're almost like our brain is picturing just this room right here, but put onto that mirror, sort of?
Okay, here's what's really happening. The light from the environment is striking the convex mirror. It is encountering your eye, but your eye is looking at it and saying, based on what I see, I know the image is not in front of the mirror, but behind it. And your brain is basically saying, I can see a little classroom behind that mirror. Just like when you see this, you know the light is over here, striking your eye, but you are behind the mirror. You exist behind the mirror. Your brain is basically creating the image behind the mirror. So when you create an image that is not where the light is, it is a virtual image. It's just as valid as a real image. It's just we need a lingo to say light here, image there. If the light's over here, which it is, and an image forms over here, which it sometimes does, it's a real image. If the light is over on this side, but the image forms on this side, which happens with a flat mirror and a convex mirror, and a concave mirror sometimes too, if the light is here and an image is over here, it is a virtual image. Now, it doesn't mean not real. It just means we need some sort of lingo to say image form where the light is not. Make sense? We move on? Hey, give me a thumbs up if you want to move on. Wave your hand around if you're going to talk about it some more. Wave your hand around if you're Aiden. Okay, cool. All right, so let's go ahead and put an object in here. There's our flat mirror. Does the object emit light? Probably not. Most fire dogs do not emit light, but the environment might illuminate them. And we see a virtual image over there. Yes?
So when you shine the light at an animal's eyes and it goes, is that just light being reflected off the eye?
Yes. There's a lot of parts of your eye that are actually reflective. Okay, so object, virtual image. Okay. Now with a concave mirror, if an object lights up, it might create a real image right there. Okay. It can actually create a virtual image in an environment that you will learn tomorrow, but right now it's a real image right there. And with a convex mirror, light strikes the mirror and light diverges, so we track back with dotted lines and we create a virtual image right here.
Wait, so flat mirrors can be virtual and real?
Flat mirrors are always virtual.
Always virtual.
Yeah.
And then concave are mostly virtual?
Concave can be real or virtual depending on where the object is. In this,
I love you. Say, Simon, go to school.
Alexa, announce, Simon, it's time for school.
Announcing.
Simon, it's time for school.
Is that for your son?
Yeah, my 5-year-old is playing with Alexa at home. But anyway, so,
Alexa.
he's late.
And he's like,
Yes, leave the house by 8:30. Anyway, so we have a concave mirror that the light basically reflects back, and this is a real image. Now, we'll see environments where we can actually create virtual images, but in this case, it's a real image.
Okay, so I'm kind of confused
Okay.
because when you have a mirror in front of you, the light is shining onto that mirror.
Yes.
The light is shining back,
Yes.
and you're looking at it, but it's saying, well, let's go behind it, but you can't see behind the mirror.
Okay.
I'm really confused.
Alexa,
It's like
you know
you're
how when
looking
you look
into
in
a
the mirror-
window.
We
Yeah.
just
That's basically what
When
it
you look in a
See,
mirror,
you're thinking of virtual image as not existing. That's not what virtual means. It doesn't mean doesn't exist. It means we need lingo to say an image is basically being formed by the data in our eye, and we're putting the image back here.
so Alexa,
Some species look at a mirror, they cannot do the math to put the image back here, and they see nothing. It's just a big mess. They can't rationalize it. You can. You can put the image behind the mirror.
So then, how does the real image work? Like, what is that?
The real image is just
I-
an image that exists in front of a mirror where the light
So it
is.
looks different than
listen, you know how
virtual?
when you look in a mirror, it looks like there's stuff like if it's a clean enough
goes
mirror,
past
you
it.
can go past it.
Yeah.
That's
oh,
why it's
okay.
virtual, because it looks like you just go through it, even though you
Even
know
though
you
there's
can't.
probably a wall behind that mirror.
AKA and a mirror in front of you.
Okay.
Unless you're in like a Disney movie, like I will step to here.
A picture.
All right, so
Silver behind
if
it.
this stuff makes sense to you, give me a thumbs up.
Yeah.
If you want to talk about it some more, wave your hand around.
Oh, is that?
All right. Now, it wouldn't be physics if there wasn't math, and there's definitely math. The fun thing is the math is really easy. The tricky thing about the math is it requires fractions. Oh no, fractions! I can't do them in my head. Yeah. Okay. So 1 over f equals 1 over do plus 1 over di. 1 over f equals 1 over do plus 1 over di.
So 2 over r equals 1 over the
And I don't know why, actually I kind of know why, we don't express this as f is 2r, but 1 over f equals 2 over r. So, or r is 2f. I don't know why they don't do r is equals 2f for mirrors. The reason they do it is because they want to teach you in such a way that you can use this information later on, and this equation has more parts to it later on. But right now you can just say, all right, I'm going to multiply both sides by r, multiply both sides by f, r equals 2f. You can say, r equals 2f. R is the radius of curvature of a mirror. F is the focal distance. So the radius of curvature is always twice the focal distance, or the focal distance, more accurately, is half the radius of curvature. Di is the distance from the device to the image. Do is the distance from the device to the object. Now, these are usually given to you in centimeters. You can use centimeters or you can use meters. because you're just adding and subtracting. The important thing is everything has to be in centimeters or everything has to be in meters. Either one. Okay. Usually it's given to you in centimeters. You can even do all as millimeters and all as kilometers if you want. But everything needs to be the same unit. All right. How we doing? Okay. Now, signs are important. Positives and negatives. Real objects get a positive, virtual images get a negative. So if it's a real image, it's going to have a positive DI, and all objects are real no matter what. DO is always positive. Okay? DO is always positive because objects are always real no matter what. DI may be positive or negative depending on if it's a virtual image or a real image. Does that make sense, what I just said? Again, we're going to do a whole bunch of practice with this coming up, but realize that just for now, take it on, just take it. That objects are always real, DO is always positive. Images may be real or virtual. If they are real, DI is positive. If they are virtual, DI is negative. What about F? Is F always positive, or can it also be negative? It can also be negative, because if you go back a few slides, you remember that the focal distance for a convex mirror, is virtual. Okay, that's the focal distance right there for a convex mirror. A convex mirror has a virtual focal point. I'll say that again. A convex mirror has a virtual focal point. Right there. Okay? So with a convex mirror, your F is going to be negative. With a concave mirror, your F is going to be positive.
What about a flat?
Zero.
Zero?
Yep.
Because there's no focal point in flat here.
Right. In other words, this is going to be 1, and you're like, you can't do divide by 0. Anyways, 1 equals that plus that. So. All right, so magnification. Magnification is the ratio of height of an image to the height of an object. It is also, because of math, the ratio of the negative distance of the image to the distance of the object. That's magnification. So, let's go ahead and label our little diagram. Right. Where would you put DI? So copy this little diagram and then predict where you would put DI, where would you put DO, where would you put F, and what would you use to find M? So go ahead and put our little fire dog diagram there. I'm sorry? Not yet. If the reflection was observed back here beyond the focal point, then it would be inverted. But the top arrow is still the top arrow, and the bottom arrow is still the bottom arrow. So on your little diagram, predict where you would put DI, predict where you would put DO, predict where you would put F, and we'll see if your prediction matches my diagram. Yes?
You know those movies where it looks like they just have concave anything goes into the focal point, but then like it shoots a giant laser out and like all of the super sci-fi movies.
Like Star Wars and stuff?
Yeah, and just anything. And then it shoots a straight beam. Is that even possible?
Absolutely.
Okay.
Your headlights do this. Your headlights are parabolic mirrors where light, you might notice that modern headlights, they look like this, and there's a little box right there.
Uh-huh.
And the box, basically, the light goes this way, and light goes boop, 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 and that causes the rays to go out parallel. And the box is there so you don't get the annoying bright spot of the lens or the bulb. So a parabolic lens can basically, or a parabolic mirror can basically take all that light and shoot it out parallel.
Just straight ahead.
That's crazy.
All right. So did you put your DO right there?
1 point in front of it, and then you can do one straight.
Yeah.
And you put your DI over there? And then if this is HO, the height of the object, that's the HI, the height of the image. Now, there's some lingo. Are you ready? There are 6 words that we use to describe images. We choose 3 of those 6. Okay, yes. So the first word we use is the image real or virtual? So when you're making images, one of the things I'm going to do is I'm going to ask you where is the image, what is the DI, what is the magnification, what is the M, and then describe the image. You will use 3 words. The first word is, will you describe it as real or virtual? What's the difference?
Real is in front of the mirror, virtual behind the mirror.
Real is where the light is,
Oh.
virtual is not where the light is.
Okay. That works.
The next word you're going to use is it reduced
Okay.
or magnified? Is it lessenized or embiggened? So, reduced, how will you know if something is reduced? Yeah, so you would say the M is less than 1, or the DI is less than the DO. That's reduced. Okay. For magnified, your M is larger than 1, and your distance of the image is larger than the distance of your object. That's, so lessenized and biggened. So bigger than 1, smaller than 1. And the last word, is it upright or inverted? Upright or inverted? How do you know if something is upright or inverted? You're like, if the top light beam becomes the bottom light beam, it's inverted. Also, in an upright image, the magnification is positive. In an inverted image, the magnification is negative. So using that information, how would you describe that? Would you call it real or virtual? You'd call it real. Would you call it reduced or magnified? You'd call it reduced. Would you call it upright or inverted? You'd call it upright. Okay, questions? In that case, we'll call it a day. We'll pick this up again tomorrow. So we didn't make it to Snell's law, so we're not doing the lab tomorrow.